All right, this is 8.6, writing and graphing exponential decay functions. We've already done growth functions, so now this is decay. So think about it in real life. What does decay mean? Our vocabulary definition here is that it's a quantity that decreases by the same percent over equal time periods. So let's take a look at what a decay graph and equation looks like. So first of all, we have y equals 1/3 raised to the power of x. So we're going to plug values in for x, and those could be all real numbers. For all equations, the domain isn't always all real numbers. I know it has been lately, so you're probably thinking that, but we'll be getting to those equations in your future where the domain can't always be all real numbers. All right, so these are the exponents. So let's go backwards. This would be 1/3 to the second power. So 1/3 times 1/3 is 1/9. 1/3 to the first power is 1/3. Anything to the power of 0 is 1. Now let's think about what to the -1 power means. That's 1/3 to the -1 power. That's the same as 1 to the -1 and 3 to the -1. So if I flip that around, it becomes 3 to the 1 over 1 to the 1, or just 3. So that's 3 there. Okay, and then the same idea if they were 2's to the -2 power. Flip it around. 3 squared is 9. 1 squared is 1. Okay, so that's why we did all that exponent work at the beginning of the chapter. So now we're going to plot those points. So it's -2, 9, -1, 3, 0, 1, 1 1/3, 2 1/9. So again, we're approaching the x-axis, but we're never going to cross it. So you're going to do your best. I'm going to do my best with my thick marker here to try to get it to not go over the x-axis. And the range then, we can't have it be 0 and we can't have it be negative. So the range is all positive real numbers. Okay, so that's what our graph generally looks like, and a pretty good idea of what the domain and range will be. Okay, example 2 is now when they plug something in for a that's other than 1. See, there's a 2 there now. So this is our table from the previous example. I'm just going to fill it in. It was 9, 3, 1, 1/3, 1/9. That's the same as the previous page. And now what we're going to do is multiply those by 2, because order of operations, exponents first, then multiply by 2. So we get 18, 6, 2, 2/3, because that's like 2 over 1, and 2/9. Okay? I'm going to show you what the graphs look like. You can plot them out, and then I will show you what the graphs look like. And since I didn't do a very good job drawing these in 8-5 with my thick marker, it just doesn't work so great. I need colored pencil. Here's what we have here. So this is our original curve on the left, and the new one is on the right. Okay, it's steeper. So we call that what? We call that a vertical stretch. Okay, the y values for the second equation are 2 times the corresponding of the original. So it's a vertical stretch. So the steeper, remember, steeper means it's a stretch. If it wasn't as steep, it would be a shrink. We say it's vertically because it's in that direction. We're stretching it in this direction. All right, so down at the bottom, now what you would do is you would graph when there was a -2 in front. So each one of those values up above would be multiplied by a negative. So I'm going to plug this in green. If this was a negative here, these would all be negative values. Okay, so the graph would look like this. Here's my original. Here's the -2 being multiplied. Okay, so this is still a stretch. 2 is bigger than 1. The absolute value of 2 is bigger than 1, so it's still a stretch, but It's flipped over the x-axis. Do you remember what word that's called? It's called a reflection. So that graph is a vertical stretch and a reflection in the x-axis. I'm flipping it over the x-axis of the original graph. And that's the descriptions that you're going to want to have for these. Okay, so example 3. Now they're going to give us the graph. We have to decide if it's decay or if it's growth, and then we have to write the rule. All right, so it says tell whether the graph represents exponential growth or decay. Write the rule. The graph represents, well, what? Which way is this going? This is going down over time, so that's decay. So this is exponential decay. All right? Remember, our general model was y equals a times b to the x. B has to be between 0 and 1 for decay. And here's our note on that for decay down here. So if the b value is between 0 and 1, it can't be 0 or 1, but it's got to be between, then you know you're having decay. Do you remember what the a stood for in the growth models? A was the y-intercept. The y-intercept is at 0, 5. So it's 5. A must be 5. Then we're going to find the b value because we're using this equation. We know a is 5. We are looking for b. The way to find that is you're going to use any point on the graph. They gave us a point right here at 1, 1. So we're going to use x is 1, y is 1, and a is 5. We're going to plug it in and solve for b, just like we did for linear equations. So 1 will equal a b to the power of 1. Well, anything to the power 1 is just itself. So this is like 5b. I'm going to show you a little more work here. Okay, so then divide by 5. So b equals 1/5. So our equation is y equals 5 times 1/5 raised to the power of x. So the 5 was the y-intercept. The b we just found right there. That's how you come up with your own equation. Okay, so just a refresher. To tell whether it's growth or decay, we talked about decay. The b is between 0 and 1. To be growth, a is greater than 0 and b is greater than 1. It also is going up as you're traveling over time. All right, so now exponential decay. We have a little bit of a typo in the notes here where it looks like the growth model. This should be a minus sign right here. So change that to a minus sign. It should be 1 minus r. We're not growing over time, we're decaying, so that should be a minus sign there. So a is the initial amount. R is the decay rate. So this is just like the growth model, but now it's decay. 1 minus r is the decay factor. And t is the time period. So we're going to use that to help us apply it to the next problem. All right, so we have a population. It's of a city, and it's decreasing from 95 to 2003 by 1.5% annually. In 95, there were about 357,000 people living in the city. You're going to write a function that models the city's population since 95, and then after that, you'll find the population in 2003. So it says let the capital P be population in the city in thousands, and let T be the time in years since 1995. So that's key to think about it, since 1995. So the initial value, since it's in thousands, we just drop the thousands, and it's 357. The decay rate, we have to change this percent to a decimal. So it goes over twice. So it's 0.015. Don't make it 0.15 or that's 15%. Now we use our decay model, and we're going to plug in the values. So A is our initials, so it's 357, and then it's 1 minus 0.015. We substituted 357 for A and 0.015 for R. And then it says to simplify. So what they want us to do there is actually do the 1 minus 0.015. So it's 357 times the quantity of 0.985. So something to remember is that if it's decay, it's going to be less than 1. Remember, it's between 0 and 1. So I have something between 0 and 1. Now to find the population in 2003, I have to see how many years that is after 95. So 95 to 2000 would be 5 years. 2000 to 2003 would be 3 more. So 5 plus 3 is 8 years. So we're going to substitute 8 in for T. So that becomes 357 times 0.985 raised to the power of 8. And order of operations says that we're going to do the exponent first. And in our calculator, it comes out to be kind of a long decimal. We're going to round to the nearest tenth, so it's 316.3. Now remember, that was in thousands, so now this becomes times 1,000. We'll give you 316,300 for the city's population. Okay, so pause the video, go down below, and work these out. See if you can get them. I'm going to flash the answer. Hopefully it'll be right, and then I'll work them out. Okay, so if you've worked these out, this was exponential growth. It's going up from left to right over time. It's y equals 4 times 2.5 raised to the power of x. And then in 2020, it'll be about 244,700. So what I'm going to do now is I'm going to actually work those out to help you through it if you're having trouble. So the first thing we need to do is plot out the points 0, 4, and 1, 10. So it looks roughly like that, okay? And it's going up over time, so I know that that's exponential growth. And then I have to write the rule, okay? So remember, it's y equals, I'm going to do my work over here, y equals ab to the power of x, where a is the initial value, or otherwise known as the y-intercept. So that's 4 in this case. I don't know the b, I have to find it. So I'm going to use the other point that they gave me to help me find it. So in this equation, x is 1, or sorry, in this coordinate, x is 1, y is 10. So it becomes 10 equals a is 4 times b, which is, we don't know, and then y is 1. And if we always do the power of 1, that's the key, because then we can figure it out, because anything to the power of 1 is just itself. So we have 10 equals 4b, divide by 4, and I'll reduce it to 5 halves. B equals 5 halves, or you could say 2.5, which is what they did in the book. So my equation ends up being y equals a, which is 4, times, I'm going to use parentheses, 5 halves, or 2.5, raised to the power of x. Okay, in example 3, or sorry, checkpoint 3, you're going to use example 4, so the one up above, and says, what would the population be in 2020? Okay, so 2020, you have to figure out how many years that is since 1995. So that is 25 years. So 25 is going to be our t. So we used our equation from before, which was population is equal to 357, 0.985 raised to the 20th power. I'm going to plug that into my calculator, and it's approximately 244.7, I rounded, and then it's in the thousands, so then it was about 244,700 people. for the population. Okay? All right, see if Mrs. Wyman if you have any questions, or head on to the next step.